there sound on it?
Yep, there's sound. All right. So number one, f is continuous and differentiable because it's a polynomial. It is continuous and differentiable because it's a polynomial. I don't know why she factored it, but whatever. Okay, shh. Okay, I'm going to go through this quick, so pay attention. So it's continuous and differentiable because it's a polynomial. Find the endpoints. You found f of 5 and f of negative 2. They both equal 0, so Rolle's theorem applies. So then all you got to do is take the derivative and set it equal to 0. And guys, every time, if the endpoints are equal, what is the slope of the secant going to equal? Every time. So all you're doing is setting the derivative equal to 0 if Rolle's theorem applies. If Rolle's theorem applies, set the derivative equal to 0 because that's what the slope of the secant has to equal, the AROC. And then you get 3/2. And look, 3/2 is on the interval. Why? Because Rolle's theorem guaranteed it had to happen. Okay? Number 2, this one is non-diff. So you can just stop. Rolle's theorem doesn't apply. Do you know why this is non-diff? Can anybody tell me? Huh? There's a cusp at where? 0. Okay, it's down to. Okay, this is a graph. This is a bird. Okay, this is a bird shifted down to. Looks like this. So there's a cusp at 0, -2. I only care about the x value because that's the interval I'm looking at from -1 to 1 on the x-axis. So 0 is non-diff, so Rolle's theorem does not apply. This one, it is continuous and differentiable because sine is continuous everywhere. It's a nice smooth curve. If I plug 0 into sine x, I get 0. If I plug 2 pi, so I'm plugging both of these in to my original function, both of them equal 0, which means the AROC will equal what? Like you get AROC, I'm going to show AROC one last time. You get AROC by doing f of b minus f of a over b minus a, which in this case would be f of 2 pi minus f of 0 over 2 pi minus 0. F of 2 pi, it doesn't even matter. Once I show these are equal, it doesn't matter what they equal because you're going to subtract the same value on top. And if you subtract the same value on top, you're always going to get 0. And 0 divided by anything is what? 0. So that's how we know the AROC ends up being 0. So then all I have to do is take the derivative, set equal to 0, and then reverse unit circle. I'm sorry, guys. You got to know your unit circle. Come on. Cosine's the what on the unit circle? The x or the y? Cosine is the what? Sine is the? Come on, we got the unit circle. Where does cosine equal 0? Pi over 2 and what? Are those answers both in that interval? Yeah, Rolle's theorem guaranteed at least 1. How many did you get? I don't care, you got 2. Get at least 1. Is everybody with me? All right, continuous differentiable. F of 1 equals 1, f of 3, and you get this. I plug in 1, I'm going to get 1 minus 2 natural log of 1. What's the natural log of 1? Let's have that memorized. What's the natural log of 1? 0. So you get 1 minus 0, which is 1. Then when you plug in 3, you're going to get 3 minus 2 natural log 3. I can't do anything to that. That's just 3 natural log. That's just 3 minus 2 natural log 3. About the best you could do to it is go 3 minus natural log of 9. You could put the monkey back in the tree. But these two things are clearly not equal, so does Rolle's theorem apply? If they're not equal, Rolle's theorem doesn't apply. MVT, you don't even have to go that far. MVT, you don't have to show the endpoints are equal. You just need to show it's continuous and diff. All right, so this is a polynomial. It's continuous at diff. I don't even care that these are not equal because that's dealing with Rolle's theorem, so I don't even know why she's doing this. I would never do that if I'm just doing mean value theorem. I would just be like, well, I guess, actually, I will do it. Take it back. I know why she's doing it because does she ask for the value? Yeah, she says find the value where mean value theorem is guaranteed. Okay, so we're going to find out what the slope of the secant is. Now, here's what you need to memorize from MVT, everybody. You need to memorize with MVT, first of all, what is required. What is required to use MVT? must be continuous on the closed and differentiable on the, let's say it again. It must be continuous on the differentiable on the open. It's a polynomial. It's continuous everywhere. It's differentiable everywhere. There's no corners, cuts, vertical tangencies. So mean value theorem definitely applies. Then here's what's guaranteed by MVT, not Rolle's theorem. Rolle's theorem takes it a step further. It's still, Rolle's theorem is still mean value theorem, but one step further. It's a special type of mean value theorem. Mean value theorem is just generic. IROC equals what? That's all you need to know. Mean value theorem. IROC equals AROC. Slope of the secant equals what? Slope of the tangent. Now, analytically, what does that mean? That means I'm going to take my f of b minus my f of a over my b minus a and set it equal to what? All right, on your calculus essentials, memorize that. F of b minus f of a over b minus a equals f prime of x. That's all you need to know for MVT. It's that simple. Get that memorized. And then also memorize that in order to use MVT, you need to be continuous on the closed and differentiable on the, because it's a non-vowel theorem. M is a not a vowel. IVT, you only need to be continuous. But your non-vowel theorems, you have to be continuous and what? Diff. We're going to learn another vowel theorem, EVT, extreme value theorem, and it's a vowel, which means it only requires it's continuous. It doesn't care if it's differentiable. The only ones that matter for differentiability are the ones that are non-vowels, mean value theorem.
Is there more than one non-vowel?
No, that's it. It's the only one. MVT. Continuous and diff. The other two are vowels, I and E. Those just require it's continuous. Okay? So, here's what you do. If I want to figure out where slope of the secant equals slope of the tangent, all I'm going to do is real quick take the derivative. So they took the derivative. Jean took the derivative, even though she's crazy. Okay? Jean took the derivative. Then she finds the slope of the secant, and then she solves it. Now, when she did this, some of you, here's where algebra goes bad. Okay? I had algebra discussions with students yesterday. All right, this is no longer calculus. When you have an equation and you have more than one like term, like you can't combine like terms. I'm doing this, I'm really hammering this with pre-calc right now. You have an x squared and an x. Can I combine those? Then you always set it equal to 0, every time. If you can't combine like terms, then you always set it equal to 0 and factor it. So what did Jean do? She moved this one over, and she actually made it 3x squared minus 2x minus 1 equals 0, and then she slid and glid, but she did all that work in her head. So she's not showing any work. So I know some of you know how to slide and glide. You can go like that, slide the 3, then you factor it and go x minus 3, x plus 1. And then you divide by what? Because what did you slide?
3.
So divide by the 3. So then you get x minus 1 times 3x plus 1. And that's how she got all that factoring. But she skipped all this work that you're not seeing, which I know drives some of you nuts, but you got to be able to do the algebra. She's skipping it on purpose. I know why she does is I've listened to her talk before. Okay? She skips it because she says calc students are supposed to know how to do that. All right? So negative 1/3 and 1. Are those both on the interval?
Yes.
Yep, and they were guaranteed by MVT. Actually, one of them's not on the interval.
Oh, I don't know, what is it?
Because the result says that it has to be inside the interval. So the value C's got to be between. So you have to cross out the 1. So negative 1/3 is the answer. So you're only looking for the answer that's between the values. Yes, I know it's continuous on the closed, differentiable on the open, but mean value theorem guarantees there's a value that exists on the interval, inside the interval, between A and B. So negative 1/3 is the answer. This one right here, I'm going to go over some algebra with you. Continuous diff, set the slope of the tangent equal to the slope of the secant, and I get here. Now, here's where algebra goes crazy. I don't care how you do this. I'm going to show you what I did with Molly yesterday that I think actually is better than what Jean does. Okay? Because a lot of you wrote the derivative like this. You have it like this. You have negative 1/2 times 3 minus x to the negative 1/2. And then you got it equal to negative 1/3. And here's the problem. Some of you are like, I don't know what algebra I should do. Now you can do what Jean did. You can move it to the denominator and make it a square root again. And then you can cross multiply because you have two fractions that are equal to each other. So she cross multiplied. like 8th grade. You can do it that way. That works totally fine. And then she divided both sides by 2, and then she squared both sides. I'll get rid of all that work for you right now. You ready? You don't need to do that. Be really good at algebra. Really, really good. I never change them back to roots. I hate roots. But I do know this. I can get rid of the negative 1/2. How can I get rid of the negative 1/2? Times by negative 2. So if I times by negative 2 the other side, so I'm going to times both sides by negative 2 over 1. That'll get rid of that. There you go. You're gone. I kind of killed it. Negative 2 over 1. That's going to give me a positive 2/3. Everybody in agreement? You ready? I don't want to move that to the denominator and have to cross multiply. So what you do is you look at this exponent. I want to get rid of it. I'm going to raise it to some power to get rid of that exponent. Here's the trick. Memorize it. Always raise it to the reciprocal power. So raise it not to the 2, negative 2 power. Because you got to get rid of the negative 2. Negative times, because the rule is power tower. What do you do with exponents when you have a power tower? Multiply them. But what you do to one side, you got to do to the other. So that'll get rid of this exponent because power tower, that gives me an exponent of 1 now. So now I'm left with 3 minus x equals, well, can I square the 2/3? What happens when you square 2/3? 4/9?
Yeah.
And then what's the negative exponent tell you to do? 9/4. Flip it. I think that's way easier. Then subtract the 3. I can't help you if you can't subtract 3 from 9/4. I can find a common denominator in my head. How about you? 12/4, thank you. So you get negative x is equal to 9/4 minus 12/4, which is negative 3/4, and then just drop the negative. So x equals what? Is that in my interval? Is that in my interval?
Yeah.
Yes, it is. Good algebra stuff here. Here's the rest of them. I really don't want to go through all of them, but they found 2 values for number 7. It was plus or minus root 3 over 2. You were able actually to solve that by square roots. When you took the derivative and set it equal to negative 2, I just multiplied both sides by x squared to get the x squared out of the denominator. And then you ended up with 2x squared equals 3. Divide both sides by 2, take square it. You get plus or minus root 3 over 2. I know 3/2 is 1.5. So if I take the square root of 3/2, square root of 1.5, isn't it going to be something smaller than 1.5? Like it's going to be like 0.76 or 7 something, right? Okay, so I know that this is going to be something between here. But you've got a plus or minus. Which one do I have to get rid of? The minus one, because it's not in the interval. I just want the positive one. All right, absolute value. I apologize to the person I helped on this and saying you had to use the derivative rule for absolute values because I forgot to check to say that this is non-diff because of a what? It's a flying V. It has a corner. This is non-diff. It is non-diff at 1/2. Wait, hold on. Oh, yeah. And that's between negative 2 and 3. So it is non-diff on the open interval. So MVT does not apply. You did not have to do any work for this one. Sorry, Molly. Huh? I lied to Molly. And somebody else, I think, too.
That was not me.
Not Molly. Not Molly. Did I do you? Who was it that I did? Was it you? Okay, I couldn't remember. All right, so Megan was the one that I lied to. I feel like it was somebody else, too. Was there a second person in there asking me about it? So sorry. I do. I know. I need to get off. I got goldfish now. You know why I have the goldfish? To remind me I'm teaching you guys. Because the average attention span of a teenager just dropped below the average attention span of a goldfish. The goldfish has an average attention span of 8 seconds. Do you know what the average teenager's attention span dropped to this year? 6.2 seconds. You're my little goldfish. Okay. All right. No, I'm just saying your attention span. It's not just for you guys. It's actually all humans. Human attention span has dropped from 12 seconds in 2000 to 6.2 seconds now. Does anybody know what's changed? Screen time. Do you know what screen time was average for humans this year? 6 to 7 hours. Do you know what it was for teenagers this past year? 7 to 9 hours a day.
How much are you on your phone?
Hey, adults are in that category too. Adults was a little less, but I have to look at mine selectively because I spend like this right here goes into my screen time.
I have to start a couple hours because my phone is on, but I'm never actually looking at it with YouTube.
Yeah.
So I just have to look.
Yeah, so mine, I look at what I'm on. I had to take my X down because I'm on X all the time. So I was like 3 hours on X a day. I'm down to like 40 minutes a day. I read my news. I follow everything. I read every side. I listen. Because I try and find the intersection of all the people that are screaming. And there's not much intersection, unfortunately. So everybody's just yelling at each other. It's ridiculous. Anyways, this right here, so MVT doesn't apply for that one, so sorry, Megan. That was my fault. And then F is, this one definitely disco curve. It's going to work great for this one. The only thing that works is negative 1 square root of 1/3. By the way, square root of 1/3, let's just review this. Some people write this as root 3/3. How did I get there? Square root of 1's 1, because you can do the square root of top and bottom, give them their own house. So you have 1 over root 3, and then multiply top and bottom by what? Root 3, and that gives you root 3/3.
It's like magic.
Yeah, it's magic. Don't forget that. We did that last year. But do you have to do that? Can you just leave it as the square root of 1/3? 1/3 is 0.3 repeating. If I take the square root of 1/3, it's just going to be like 0.1 something repeating. It's still going to be between -1 and 0. And you want the negative one, not the positive one this time. This one right here, it is continuous and differentiable in the open. The only place natural log is not, remember, what's that page, continuity page? Is it page 49?
Yes.
Is it page 49 that we always flip back to? Let's get that memorized. Is it page 49? Huh?
It's 49.
It's page 49? Wow. Is it possible at the very bottom to multiply two continuous functions and still be continuous?
Yes.
Now, x is continuous everywhere, but ln x is not. Can anybody tell me where ln x is continuous? It's an R curve. Very good. Where it's positive. From one, remember, it crosses at 1, 0. ln x is continuous, x greater than 0. So if x is continuous everywhere, and ln x is continuous, x greater than 0, is it going to be continuous from 1 to 2? Yes, you're good. So this one works. So set your I rock equal to your A rock and blah, blah, blah. All right, this right here, Mr. O ran the Disney Marathon in 2 hours, 18 minutes. By the way, that's pretty good. It used to be really good, but now women run that fast. The woman's world record now in the marathon is like what the men used to run. It's just getting crazy. They think a woman is now going to break 4 minutes in the mile. The world record is 4:07. They think that they're going to be able to get a woman to break 4 minutes in the mile. And the reason that's such a big deal, when Roger Bannister first broke the 4-minute mile, they warned him not to do it. They said, if you break the 4-minute mile, your heart might explode. So they told him, you're doing this at your own risk. You know what the world record for the mile is now? 3:43. 3:43. Do you know that an American just broke the world record for the 5K? This is a big deal because it's the first non-African to do it, to hold the world record in the 5,000 meters. His name's Grant Fisher. He makes millions of dollars, just signed a multi-million-dollar contract with Nike. He's awesome. Y'all should follow. He's so cool. He just ran 12:43 for the 5K. Now listen to this. 12 minutes and 43 seconds for 3.1 miles. That's an average of 4 minutes and 1 second a mile for 3 miles. Go to the track, run the track, 1 lap, 60 seconds. He did that for 12 and a half laps. And they used to think you couldn't break a 4-minute mile. They think now that there's going to be the 4-minute mile broken 3 times in a row. A guy just ran the marathon. He just broke the world record of the marathon. He ran the marathon, the half marathon. He ran the half marathon at an average 5K pace at what the 5K world record was 20 years ago. He averaged 420 something a mile for 13 miles. And he ran his last mile in like 4:04 for a half marathon. It's wild what they're doing. It's actually crazy. All right, yeah, it's wild. So just imagine, he's running 15 miles per hour for a half a marathon. He's running that fast. So go on the treadmill, try and run 15 miles per hour. See how long you can do it. For how long you can do it, and see if you could stay with him. I always tell my runners, I'm like, okay, guys, here's the deal. Bjorn, you're really, really fast. His PR in the 400 is 49 seconds. Bjorn's, he has the fastest. He's our school record holder and everything from 400. Well, he's hopefully going to be in everything in 400 up. So Bjorn runs about 50 seconds for the last 400, or 400. The last lap of the 10K race at the Olympics, it's 25 laps. 25 laps on the track. I'm like, Bjorn, you could win it if you let them run the first 24 laps first, then jump on the track and try and out-sprint them the last lap. So they're going to run the whole 25 laps. You wait until they get done with 24 and see if you can beat them, because they'll run their last lap in 51 seconds. So if Bjorn's not on it, if he's not running his very best, he might not win in the last lap after they've run 24. That's how fast they're running.
Some of them kick so late that Bjorn probably wouldn't see the chance.
No. No, do I think Bjorn can get that good eventually? Yeah, probably. We'll see. Takes a lot of luck. You got to stay healthy. Running such a...
Bjorn when he's not here.
Oh, yeah. Shout out to Bjorn. Okay, good luck, Blake and Bjorn.
You think he'll watch the video?
No, he will. He actually will. Mr. O, Blake, I don't know. Mr. O ran the, Blake, if you watch this video, let me know. Mr. O ran the Disney Marathon in 2 hours and 18 minutes. Remember, a marathon is 26.2 miles. The marathon world record now is 2 hours and 1 minute. Yeah. Show that at least twice he had to be running at a rate of 11 miles per hour. This is the kind of problem they do on the AP exam, and you have to know what theorem to use.
MVT.
Well, what you want to do is you want to show that he had to be running at a rate of 11 miles per hour. So first of all, you figured out what his average velocity was. If he does 26.2 miles, 2.3 hours, and you got the 2.3 hours by converting 18 minutes to what? You had to convert 18 minutes to what? Hours. How many minutes are in an hour? 60. So you just did 18 divided by 60. So you got 2.3 hours. So what she ended up with, Gene ended up getting an average velocity of 11.3913 miles per hour. So listen, if he had an A-Rock, if Mr. O had an A-Rock of that, and since he's running, we're assuming that this is a continuous function. Okay, he runs the race, he starts, he finishes, and that time is continuous. Okay, they don't allow him to stop his stopwatch. In a race, do they allow the time to stop? So we'd assume the time is what? Continuous. So since Mr. O would run at 11.39 miles per hour on average, he would be running at 11 miles per hour when he speeds up and slows down again. So if he averages, is there going to be a time where he's actually going 11.3 miles per hour? Yeah, so that's the A-Rock parallel to the... That's the A-Rock parallel to the I-Rock. That's the slope of the secant equaling the slope of the tangent. Now, we actually can't do this, but they just wanted you to explain that it has to happen.
Can you also say like that by IVT? Because you can't say that.
You could say it by IVT. Actually, you could prove this one with IVT, saying that if you average 11.3, you would have had to go faster than 11.3 and slower than 11.3. Therefore, you had to go through 11.3. It's a little harder to explain with IVT because I don't have the equation to show that it went faster than L, because IVT requires you to show that it's bigger and smaller. So MVT is a little bit easier to use here. Okay. This one, Sissel's Automobiles, same kind of thing. You have a function this time. Now this one you could definitely prove. You're just going to set the A-Rock equal to the I-Rock, and you get about 3.2915, which is about March, is when the average rate would equal the instantaneous rate of change. They love table problems. Let me actually read through this one and do this one with you. Contaminated water is being pumped into a retention pond. RFT is the amount of water. That actually happened at my mom's house when this flood happened, Hurricane Helene. They just now, last month, finally were allowed to start brushing their teeth with their water again. My brother, since Hurricane Helene happened, you could not brush your teeth if you were on city water because the water was contaminated. If you went to a restaurant, they were serving bottled drinks and canned drinks, and they were using plastic utensils because the water was contaminated this long. It just got cleaned last month.
They had to pay for their water then?
Huh?
They had to pay for their water?
Yeah, they had to do bottled water. So when you went to the restaurant, you had to pay for bottled water if you wanted water.
Wash the dishes that I cooked stuff with.
Yeah, they had to sterilize. It was crazy what they were doing. I don't know exactly how they were doing that, but I know that they were having to do some kind of goofy stuff with sterilization and whatnot. Yeah. So, anyways, so that's like a retention pond. If water gets contaminated, they'll move it until they can get the water uncontaminated. They have to treat it, whatever. RFT is the amount of water that is left in the pond at time t measured in hours. So you've got a chart here. We've got the retention pond. Water is being pumped from contaminated water is being pumped from the retention pond because they're probably going to treat it. So you started with 20,000 gallons, and after 24 hours, you got 5,600 gallons. Using the correct unit to measure, find the average rate of change from 3 to 21. So they're just wanting you to figure out the AROC. That's it. That was easy. Part B, estimate the rate at which the water is being pumped at 4 hours. I can't figure out what it is at 4 hours, but I can estimate with what? AROC. You estimate with AROC. So they just used 3 and 6 to estimate what the derivative would be at 4. So use the AROC from 3 to 6, and they found it to be negative 333.333 gallons per hour. And then finally, we get to the MVT part. Is there a time interval from 9 to 12 where R prime of t would have to equal negative 500? Well, if I can show from 9 to 12 that it equals negative 500, and I know that they told me that this was a continuous, no, they didn't tell me, but we're going to assume since the water's being drained, they're not turning the pump off for 24 hours. So we're going to assume it's a what? Continuous function. So if we say R of t is continuous and differentiable, we find the AROC is negative 500. Therefore, by MVT, there exists a value t on the interval between 9 and 12. Not the endpoints. Has to be between 9 and 12, such that R prime of t is equal to negative 500. This is exactly how you have to be able to write it on the free response. Right there. You should definitely know how to do that. That is going to come up. And here's the cool part. They never even make you find the value on the free response. You just have to be able to show that it exists. So this part where Gene's actually having you find the value in those other problems is not even realistic unless it's a multiple choice. On free response, I've never seen them have you actually find the value. All right. You got that? All right, let the fun begin. This is my favorite. My favorite. I don't care about the next page. All right, today, EVT. Our second to last theorem in this class. We have one more theorem after this. It's called FTC. And somebody's like, oh, you said there wasn't another vowel theorem, non-vowel theorem. There is, but it has nothing to do with what we're talking about. It's actually going to have to do with how to take an integral. It's not an existence theorem. All right, EVT. You'll like this. It's pretty simple. It's just a lot of work. We're going to be doing sign analysis like it's going out of style. Okay? No, like it's coming in style. You're going to do probably close to, in the next 2 weeks, and I'm not exaggerating, 150 to 200 sign analysis.
You said I would like this.
Okay? So you're going to get good at seeing the signs alternate and plus, minus, plus, or minus, plus, plus, and this, that. Okay? All right. EVT. We talk about the extreme value theorem. Take good notes today. Okay? This is big. This is like, I'm saying 7 to 10 multiple choice questions, and for sure going to be multiple parts on free response. Okay? This is big. Like, you can increase your score on the AP exam just knowing how to do what we're doing the next week by quite a bit, because they're going to have lots. In fact, I'm going to start assigning practice multiple choice here. And as soon as we're done with this and we start integrals, I'm going to start assigning. The first one I'm going to assign is the 1997 multiple choice exam. And you're going to see, and pretty much the first ones I'm going to assign are going to be a lot of these types of questions. Okay? All right, extreme value theorem. Huh?
Is there an answer key?
I have an answer. I work them out in the morning too. That's when, like Kate and Dawn, the guys last year took class, said that's when you feel like you learn the most, because you start to see, you're practicing the actual AP problems. And you're like, and as you go, you reinforce, oh yeah, I remember how to take the derivative of this. I remember how to do this. And it just becomes second nature. These kids are like, oh yeah, this problem, we do this. This problem, we do this. And it just gets to be like you're almost walking. But right now, you guys are on your backs and you can't even roll over. Here we go. The maxes and minimum values, extreme value theorem. Don't worry, we'll get you to stand it up here soon. The max and min values, all right, are called the extreme values. That's why it's going to be called the extreme value theorem, EVT, because it's going to help you find what? The extreme values. Do you think maxes and mins matter in the real world? I promise you, KLN's thinking about how they can maximize profit. I tell you, KLN's thinking about how they can minimize expense. Okay? I'm telling you that any manufacturing company is thinking about how they can maximize time and maximize their time, produce the most product in the amount of time given, also minimize time for employees. Okay? I'm going to tell you, if they can figure out a way to do the job, instead of using 10 people, if they can do it 5 people, they're going to do it. Because if they can do that, that will minimize costs. They're going to think about how to minimize materials, don't have waste, so that when you throw things away, like if you're on a job site and you're building a building, we don't want to have a lot of leftover lumber. We want to minimize. We want to use as much of the materials that we have purchased. Okay? So there's a lot of planning that goes into this. So extreme values or extrema, that's we also call it extreme values or extrema. The singular is extremum. I guess that's how you pronounce it. I never use it. I just talk about extrema. The process to find this is referred to as optimization. Okay? There'll be times when we want to find the max or min for X on the entire domain, and there's other times where we want it on a particular domain. When I say the entire domain, there's going to be times where I say, let's just figure out the max and min from negative infinity to infinity. And there's going to be times where I have to restrict the domain so the function's continuous. Okay? Here we go. Definition of absolute or global extrema. You use both words. I've seen them use both. I've seen them use absolute or global. When we talk about the absolute max, it's also referred to as the global max. When I say the absolute max, that'd be like saying, who is the richest person on planet Earth right now? Elon Musk. It was Jeff Bezos, but it's not anymore. It's Elon Musk. He is the richest man on planet Earth. That is the absolute or global max. Now, it's really hard to figure out how the absolute min is. Who's the poorest person on Earth? I don't know. Who has the most debt? Oh, I don't think you can probably measure that.
Do you think homeless people have debt, or do you think they got bankrupt?
I don't know. They might be. They could declare for bankrupt. We could do this though. We could measure in this classroom everybody's bank account in here, and we could say who has the most money in the bank account. But that's not absolute, because that's only talking about the people in this room, not all the people on planet Earth. Okay, so that would not be talking about the absolute. We could talk about the richest person in Perm, probably Kenny Nelson. That's not the absolute. Okay, probably. Okay, I'm going out on a limb. All right. All right. So absolute, global max. All right. If you have a function on an interval I, so there's going to say there's some interval I from A to B, whatever. You with me there, Hunter? And y equals f of c. Then f of c is the absolute max on the interval if and only if f of c is greater than or equal to f of x for all x in that interval. That makes sense, as long as it's the biggest one. If that y value is the biggest one on that interval, then it's the absolute max. It's the absolute min on I if and only if f of c is less than or equal to f of x on I. Does that make sense? Now, here's an interval. Look at it. Can you tell what the absolute max is?
Yes.
Which one is it? This right here, E, would be the absolute, and you can abbreviate it this way, and you are allowed on the AP exam, ABS max. Can you find the absolute min?
Yes.
Yes. Which one is it? D. The absolute min. Now, what I'd like to talk about is, could it have occurred at any of these other points?
No.
All right. It could have occurred at any of these other points. Could it have occurred at B?
Yeah.
As long as it would have went lower. Could it have occurred at C? Could it have occurred at D? Could it have occurred at E? Could it have occurred at one of the endpoints?
Yes.
Could this have went lower than the rest of them? Could this have went higher than the rest of them? So here's the thing I want you to keep in mind. Absolute maxes and mins can occur at endpoints, and they can occur at what's happening in between the endpoints. Can you tell me what's special about all those other points?
They're all special.
They're
Huh?
zero.
They're all special.
What is special about them? They are all special. You are correct. What is special about B, C, D, and E?
They're relative mins or maxes.
They are relative maxes or min. That's true.
What about B?
They could have a slope of 0. Some of them have a slope of 0. Which ones have a slope of 0?
C, D,
C. C has a slope of 0. What else has a slope of 0? D has a slope of 0. What else has a slope of 0? E has a slope of 0. Anything else? Wait a second. You guys said they're all special. And I agree with you.
Is it cusp?
It's a cusp, so the slope of the tangent's not 0. It's what? It's undefined. It's a point of non-differentiability. Corners, cusps, vertical tangencies. So wait a second here. Maxes and mins occur where slopes of 0, so where your derivative equals 0, or where your derivative is what? So our points of non-differentiability are going to be included when we find maxes and mins. In fact, those are going to be very important because they could occur. What else was the other ones? Your endpoints. Now, you don't know anything about the derivative there. You're just going to be given the endpoints, so you're going to have to check them. So that brings up the next part, which is what Logan talked about, is the difference between absolute extrema and relative extrema. Relative or local would be like saying that Kenny Nelson is the richest person around. Yeah, relative to this area of the world, local to Perm, but he's not the richest person on planet Earth. He's just the local extrema. So all of these can be referred to relative maxes or min. So relative to this area, is this the lowest value? Relative to this area of the function, is it the highest value? Relative to this area of the function, is it the lowest? Relative to this area, is it the highest? So those can all be referred to as relative maxes and min or local maxes and mins. Go on to the next page. Definition of a relative or local extrema. If there's an open interval C, if there's an open interval containing C for which f of C is a max, then f of C is called the relative max. So on an interval, if you can find an interval, like if you go back up here, can we find an interval where that value is the largest?
Yes.
Can you find an interval where that value is the smallest? That's what makes it a relative max or a min. So if there's an open interval containing C where f of C is either a max or a min, then you either call them relative maxes or mins. That's not too hard to see. All right? Noteworthy thoughts, I guess Gene thinks. We say that an open interval containing C means that we can find some interval A to B, not including the endpoints, where C is between A and B. Okay? That is, C will be contained somewhere inside that interval, not being the endpoints. A relative extrema is slightly different than an absolute extrema. We already brought that up. All that's necessary for a point to be a relative max or min is for that point to be the max or the min on some interval of x around C, which I've already talked about that. There can be smaller or larger values of the function at some other location, but relative to x equals C, f of C is the smallest or larger than all the other values of the function in the neighborhood of C. All right, all that's pretty obvious. All right, let's jump in. In many cases, we'll be asked to analyze both the open and closed intervals of functions. Consider the graph. So here we're going to look at one with an open interval. This actually goes from negative infinity to infinity. Now, what I want you to notice is, first of all, there's multiple extrema here. There are multiple relative maxes and mins here. At 3, -8, you would call this a relative what? You'd call that a relative min. What about the 0.22? You call that a relative max. What about the 0.40? You call that a relative min. So I'm going to put and 4, 0. So how many relative mins are there? How many relative max are there? 1. Now, considering the domain for G, which is all of it, from negative infinity to infinity, So the domain for this function is double bar R. It goes to the left forever, it goes to the right forever. Agreed? Considering the domain for G, by the way, everybody's like, oh, this is your favorite part, Mr. Morse. Don't worry, it's coming. It's not this part. EVT is not my favorite part. It's the part coming tomorrow when we get into sign analysis and maxes and mins and finding them and then doing increasing and decreasing and concavity. That's my favorite part. All right, consider the domain for G. What are the absolute extrema? Now, here's the interesting thing. These are the relative maxes and mins. Some of these are a little bit more special than others because some of these can be classified as the absolute extrema. Now, notice, are you going to get both an absolute max and an absolute min here?
No.
No. Why not?
Because it goes to infinity.
This thing goes up forever, so which one are you not going to get? You're not going to get an absolute max because the graph goes up forever. So there's no absolute max, but is there an absolute min? So there is no absolute max, which is going to lead us to EVT here in a second. But there is an absolute min. What's the absolute min?
-3,
Because that is the absolute lowest point. So if you have an interval from negative infinity to infinity, are you guaranteed both? Are you guaranteed both? No. Could you have both? Maybe, but you're not guaranteed both because the next part is actually going to show you what you need to do to guarantee both, which is going to lead us to EVT. Now, what's the difference between this function and the last function?
It's a closed interval.
I got a closed interval. I have a closed interval. So let's do all the relative maxes and mins. First of all, relative max and min. Give me one. I have a relative min, first of all. What is it? Uh-huh. All right, what else we got? I think a relative max pops up next. What is it? 7, 7. Good. And then I think I have a relative min again at where? 10, 2. Been nice it'd have been 10, 4. All right, so we got this. By the way, what's the derivative right here? What is f prime right there? Undefined. What's f prime right here? 0. What's f prime right here? 0. So we have f prime as either 0 or undefined if those peaks or valleys. Agreed? That's going to matter because I'm going to teach you something called a critical value here in a second. All right, now we go to absolute max and absolute min. We do have an absolute max this time. What is our absolute max? 7, 7. We have an absolute min as well. Where's our absolute min?
2, -2.
Now, why did we get an absolute max, not man? Why did we get an absolute max and an absolute min this time? You close the interval. Now, here's the deal. Some of you are like, what if it doesn't occur at the endpoint? Could it have occurred at one of the, what if it doesn't occur at one of the interior points? Could it have occurred at one of the endpoints? So what you could happen, if this doesn't end up being the lowest point, or this doesn't end up being at the highest point, I promise you it'll happen at one of the endpoints. The endpoints will cover it. Question?
We don't put the endpoints for relative.
No, endpoints never are considered relative. Good question. Only peaks or valleys. The only thing that's ever considered relative is peaks and valleys. Now, absolutes can occur at endpoints because absolute is just defined as what's the largest value and what's the smallest value. Relative is defined as on an interval. You can't get an interval at an endpoint because you can't get a neighborhood around it because you don't have a left side to it. Okay? Good question, though. All right, now, what conditions would absolutely be necessary in order for them both to have an absolute max and an absolute min? That leads us to our final theorem, EVT. It's not my favorite, but it gets into tomorrow. Here's the requirement. It's a vowel theorem. What's the only requirement for vowel theorems? If it's continuous on the closed interval from A to B, then F has to have a max and a what? Now, I'm going to teach you something because this is definitely going to be covered. Okay, so now, here's what we do. When we do EVT, you're going to have to do what's called the candidates test. You need to know this for the AP exam. It's called the candidates test. You are going to have to check two things to see if you have an absolute max or an absolute min. What did we just say an absolute max and an absolute min could occur at? A peak or a valley, which is on an interior point, which could be where the derivative equals 0 or what? So you're going to have to find all interior points where the derivative equals 0 undefined. Those are going to be called critical values. And you're also going to have to check one more thing. Not just the interior points, you're going to have to also check what? Endpoints. You're going to check interior points and endpoints. That's going to be called the candidates test, and it's going to be your justification for EVT. Okay? So, EVT, if f is continuous on the closed interval from a to b, then f has an absolute max and an absolute min. Here we go. Extreme values can occur at interior points or what? Endpoints. A function may have both a max or a min over an interval, either a max or a min, or no extrema on an interval. Let's explore some examples. I'm going to do this fast. Look at that one. Is it continuous? So you're not guaranteed a max or a min. You could. It could happen, but you're not guaranteed. Does it happen, though? Is there an absolute max? Yes. Is there an absolute min? Yes. It happened. Didn't have to happen, but it did. Okay? All right, what about this one? It's not closed. Is EVT going to fail?
Yes.
Why is it going to fail?
There's a jump.
Because of the jump. See, there's a max, but is there an absolute min? Why not? Because there's a hole there, and you can keep getting closer and closer and closer and never what? Get there. So there is no... This one had EVT fails, but there's still an absolute what? But absolute max min occur still. Part B, does EVT fail?
Yes.
EVT fails, only absolute what? Only has an absolute max. Okay? I don't care if you write this down. It's up to you. We just need to think about it. Does EVT apply here from 0 to 3? What does it say? F has to be continuous on the closed. Is it continuous on the closed?
Yes.
Is it continuous on the closed? Definitely not. It's open here, and there's a vertical asymptote at 3, so it is definitely not continuous on the closed. So will EVT apply? No. EVT what? Is there a max or a min on this one? There's neither. You can't get a max because you can keep getting closer to this. And this goes what? Down forever. So definitely not a max or a min. What about D? Is it continuous on the close? Is it continuous on the close? No. So EVT what? Fails. But is there an absolute max? Is there an absolute min? That's just per chance. Okay, I miss Kristen. All right. I can't just say per chance. So the EVT theorem, here we go. We're going to do this quick. I need to get this done. The EVT theorem gives us the knowledge when extreme occur, but we'll find out how to do it algebraically next without the benefit of a graph. So the next question should be, how can we identify all the extreme values? I said we're going to have to check endpoints and what? Interior points. Interior points are where you have peaks and valleys. And you can have two types of peaks or valleys. You can have peaks or valleys where the derivative equals what? That's horizontal tangents, where it's nice smooth curves at the top and bottom. You with me? Or if you have points of non-differentiability and you get cusps and corners and vertical tangencies, that'll be where the derivative is undefined. So we're going to have to find both. So when we do this, the first thing you're going to do is you're going to use EVT and show why it applies. First of all, let's look at this. Part A. Look at the equation. Look at the closed interval for from -4 to 4. Does EVT apply? Is this function continuous without looking at a graph? Remember, we're checking for continuity. We're checking for holes, jumps, vertical asymptotes. Jumps only occur at piecewise. Is this piecewise? All right, holes and vertical asymptotes occur when you have 0 in the denominator. Do we have 0 in the denominator? Where does it occur at? So does EVT apply? So put no. X equals 2, not continuous. Therefore, EVT does not apply. Look at the next one. What is e to the x minus 2 plus 1? I can't believe it. I'm hurt.
Isn't that continuous?
It is continuous. What kind of curve is it?
J curve.
It's a J curve. Is it continuous everywhere?
Yes.
EVT applies.
Is that all we have to say for these?
For right now, yes. What about the next one? What about the next one? Shooting star times a regular one. Where's the shooting star not going to be? Anything less than or equal to negative 2 here is going to be a problem, isn't it? Because that would give you a negative underneath the root. Because you want what's underneath the root to be positive. How did I find that? I just took x plus 2 and said it had to be greater than or equal to. Sorry, I did that wrong. It should be x is greater than or equal to negative 2. My bust. Everything greater than or equal to negative 2 is good, correct? As long as it's greater than negative 2, we're not going to get a negative underneath the square. Do you agree?
Yeah.
All right. Is that going to work then?
No.
No. EVT does not apply.
No.
Okay. Critical number. I got to do this fast. Golly. Critical number. Critical number for a function, if x equals c is in the domain, it's where the derivative, we already said this, it's where the derivative equals what? 0, or where the derivative is what? Undefined. When you find where the derivative equals 0 or undefined, it's called a critical point. I'm going to skip right to the candidates test. I'm going to show you how to do this real quick. And I'm going to let you tonight work on your AP Classroom, but you are going to try to do a couple of these examples. So just like 1 or 2, not ton. I'm going to let you work on your AP Classroom. Here's how you do this so we can come in tomorrow and pick up where we leave off. Right here. What you're going to do first is you're going to find CVs. You're going to find CVs. All CVs are is where the derivative equals 0 or what?
Undefined.
So you're going to take your derivative and see if it's ever equal to 0 undefined. What is the derivative of part A? 24x squared minus 6x minus 9. All right, is that okay? Then all you do is set it equal to what? 0 or, first of all, undefined. Is it ever going to be undefined? No, you don't. So then you're just going to set it equal to what? And you're going to have to factor it. I would like you to finish this one, factor it, set it equal to 0, and finish finding it. And then what I'd like you to do, and this is all you're going to do tonight, I'd like you to take those answers plus the endpoints, plug them into the original function. The largest will be the what? Max, and the smallest, not relative, the largest will be the absolute, the smallest will be the, man. I'm going to go over AP Classroom in the morning, so I'm having an early morning session for extra credit. 7:30.
Oh, earlier.
Not the early one yet. We'll get there.
I don't wake up until 9. That is early.
It's making you disciplined. I'm creating some discipline in you.
Are we just doing that one